Hello everyone. So now we're starting the next few sections, and the goal of these sections is to now find a way to compute these limits, but algebraically. Because so far we looked at limits when the function was defined by its graph, and then the computations of the limits are not really computations. You just look at the graph and you see how high the dot is, or the white dot is, or if there's a vertical and horizontal asymptote that gives you the answer. And then once the function was defined algebraically, the first trick that we've learned is, well, if you want to know how the function behaves around 2 on the left side, well, just pick some values nearby smaller and look at outputs. And this was giving us a numerical method to guess limits. But now we want to compute limits. And 2.6 is, of course, the first step there. So from now on, all the formulas are going to be defined algebraically, and we're going to compute limits. So the first section is about the basic stuff, so the basic limits. And in a nutshell, the 2.6 is telling us if you have a formula in front of you and you have to compute the limit and you want to compute the value and not guess it, just try it. Just plug your number in, and if it works, it works. And if it doesn't work, at least it will tell you how it doesn't work, and then we'll see a special approach depending on how it fails to give us an answer right away. So the first definition here is just a bunch of basic laws. Suppose we have like a bunch of real numbers, C, A, and N. N is a positive integer though. Suppose that we have a function where the limit to around A is for F is L, and the limit around A for another function G is M. Now let's look at some basic laws. So the first one is, if your function is a constant, the limit around a point will be, of course, at constant value. And this is not too difficult to see here on the graph. I have an example here of a constant function. So I have my constant function here, y equals c, and I want to study the function around A. Well, of course, here, if you look at the right or left limit, so if you choose small numbers, let's say on the left side, like you're approaching that dot, that blue dot. Same thing on the right side here. So you can see that from the left or from the right, every output will be at C. So the limit is obviously C. So the limit is C here. There's really nothing to do. So the limit of a constant is a constant. What about if you have the function x? If you have the function x here, so I drew it here again for you. So I drew the graph of the function x. So y equal x is a straight line, slope of 1, going through the origin. And I want to know what's up around A here. So of course what will happen here is that if you look on the left or right, so here, left side, you're going to that blue dot, right side, you're going to that blue dot, and of course the height of the blue dot, because y is equal to x here, is equal to A. So the limit as x approaches A of x is just A again. Okay, so basically if you're around A, you're going to be around A. So if the x is around A, the y is around A also. Nothing deep here. So that was for the second law. Now the third law is, suppose we know the limit of f is L. What happens if you multiply it by C? Well, the limit is going to be multiplied by C. So this is just the limit of C times f is just C times L. If you have the limit of a sum, if you know that the limit of f is L and the limit of G is M, then the limit of f plus g is L plus m, so you just add the two terms. What about if you take the product, if you have E times g, well, you just get L times m, so it's really just doing the exact same thing as it's supposed to be. So 6 is the first one where you have to be a little bit careful, because we're going to divide f and g here. So what happens if you're computing the limit of f over g? Well, it is going to be the quotient of these two things, L over m. Of course, assuming that m is not 0. If m is 0, then you're going to get a division by 0, and that's going to be bad. And there's a whole section just about, okay, division by 0. And we'll deal with that later. In this section, everything will work very well with the basic laws. Now, what happens if you take a function to the power n? Well, the limit will be raised to the power n. Now, the last basic law that will cause us trouble at some point. What happens if you're computing the limit of the nth root of the function f? So there's two scenarios. Either you're going to get a number or you're going to get undefined. So the first one is you're going to get the nth root of L if n is odd. If n is odd, like for example, a cubic root, it does not matter if you're computing the cubic root of something positive or negative, it works. And the other case where it works with no problem is if the inside is strictly positive, cubic root, fourth root of strictly positive numbers will work also. So everything is nice. So that's the good scenario, the scenario that makes us super happy, okay? But there's another scenario that is actually kind of good in the sense that it's not bad because we know what's happening. You're going to get undefined, okay? You're going to get undefined if you're computing the even root of something strictly negative. So even if this is giving us undefined, this is still good. Okay, so if you have, for example, the square root of -1, it's undefined. The only one that this is not covering, these scenarios are not covering, is what happens, okay, and this will be a bad case. What happens if you're computing the nth root? So you have to be careful here. What happens if you're computing the nth root of 0 for n even? This is actually going to be a bad case also that we're going to study, okay, later. So the nth root of 0, where n is even or a division by 0, are two bad problems that we're not going to deal with in this section. In every single example that we're going to go through here, it's going to work. Okay, so in a nutshell, and this is really, really important. So when you have a limit in front of you and you want to compute, not guess, you want to compute the value, the first thing you do is you evaluate, okay, your function. So you just plug your number in and you hope that you're going to be simply using one of the laws above to get your answer. So simply, even a simpler way to say it, just evaluate. Okay, so, and if it works, it works. All right, let's do some examples. So here we go. First example, let's compute the limit around 3 of 2x cubed minus x plus 5. So you plug your number in, and so you just try it. So just a regular evaluation here. So this limit will become 2 times 3 to the power 2 minus 3 plus 5. And if you do the computation here, 3 squared is 9 times 2, that's 18, minus 3, that's 15 plus 5, and that's 20. And that's it. So if you were like to do two tables on the left and right side, they would all be going to 20. Okay, so the left or the right limit would be 20. So let's do another example where it works well. So very straightforward evaluation here. Let's compute the limit as x goes to 3 again. Now we have a quotient, 2x squared minus x plus 5 over 3x cubed minus 2x squared plus 1. So if you just try it, so you get 2 times 3. Of course, here you can see I'm lazy. The numerator is the same as earlier. So you're going to get a nice 20 at the numerator. You just have to compute the denominator here. So 3 times 3 cubed minus, so the only thing when we have a division to worry about is, are we going to get a division by 0? So here, if you do the math here, you can check. This is going to give you 20 over 64. So nice fraction. As long as you don't have a division by 0, you're done. So very simple. Like, to some extent here, we're just computing outputs. This is really what's going on here. For basic limits, of course, most questions will not be basic. So let's compute the limit around 2 now of the cubic root of x cubed minus 9 over the square root of x squared plus 5. So cubic root will not cause us any trouble. The even root, we don't want something negative. We can kind of foresee that it won't be here. So you get the cubic root of 2 cubed minus 9 over the square root of 2 squared plus 5. 2 squared plus 5. So for the numerator, we're getting the cubic root of minus 1. The denominator, we're getting the square root of 9. And this will give us minus 1, the cubic root of minus 1 is just minus 1 over 3. So we're getting a nice number at the end. Okay, so good again. So nothing crashed here. And now for our last example, where things will crash, but in a good way, in the sense that we'll be able like to get the value of the limit just by evaluation here. So let's plug 2 inside. So we get 2 cubed minus 9 square root now over the cubic root of 2 squared plus 4. If you do the denominator first, 2 squared is 4 plus 4, that's 8. The cubic root of 8 is actually just 2. The numerator, you get 2 cubed, which is 8 minus 9, you get minus 1. But now we have an even root of something negative. Again, that's not bad. It just means that because the inside is strictly negative, that your limit does not exist because the whole expression is undefined. And that's the answer. Okay, so just by evaluation here, we're getting our outputs. But of course, like as I said, this is just the beginning. Of course, these examples, we get them by straightforward evaluation, but bad cases are coming. They are rising in the dark. Anyways, bye-bye.